This is lecture 4B for Calculus 1 on the Newton-Raphson method. In this class, I'm going to present two numerical methods for finding the roots of functions. The one I already presented was the one based on the intermediate value theorem, and there was a lecture on that. Intermediate value theorem was a way to find roots by realizing that for a continuous function, if you have a positive value and a negative value of the function somewhere between those two values of x, there was at least one root. Okay, here we're going to discuss another method that's Newton-Raphson method, and it's based on the slope. So the problem you would be presented with would be to find the root of an equation. Sometimes you're given the equation. For example, you might just be given that equation, the cubic equation, and you were supposed to find the value of x, or you want to find at least one of the values of x, for which f of x would be 0. X cubed minus 2x minus 5 would be equal to 0. The other way these problems present themselves is that you want to find the value of an irrational number. Like you want to find the square root of 2, and that's what I did in the other example. So you want to find where x is equal to square root of 2. And here's how you do it. You set up a function for which the square root of 2 would be the answer. In this case, as before, we could say f of x equals x squared minus 2. The square root of 2 would satisfy that equation. That would, at that point, it would be equal to 0. So here's how the Newton-Raphson method works. It uses the linear approximation to the function at some point x1. So x1 is your guess. And you make a linear approximation to it. That is, you construct the tangent line. Then you find out where that tangent line is 0. You find the root of the tangent line. Okay, that's your first estimate. You go back and check that x2 out in the function and see if it's close enough to 0. If it is close enough to 0, then you've got your root. All right, remember, these are numerical methods. You're not going to get exactly 0. You're going to get close enough to 0, and you decide how close that's going to be. It depends on the accuracy of the machine you're working on, the computer that you're working on. Depends on the results. Depends on how many iterations you're willing to try. Okay. So if it's close enough to 0, if the function is close enough to 0 at this x2, then you're done. If not, you use f2 as your guess, construct another linear approximation, find out where that linear approximation, where that tangent line is 0, and then you'll get an x3 and check the function out at x3 and see if it is close enough to 0. So those are your iterations, and again, being a numerical method, you just keep repeating these iterations until you arrive close enough to the solution. Better to see this with a picture. Okay, here is your function, is in this blue line, and you're really looking for this value of x where it crosses the x-axis. At that value, the function is 0. You're looking for that. So here's how you find it. You have your first guess. They call this just xn in general, but we could call this x1. So you pick some value, this x1. Remember, you can't see this graph. If you could see the graph, obviously you would pick something closer, but in this case you pick this value of x. And now you construct the linear approximation, which is the tangent line. It's the first two terms of your Taylor series approximation. So you have the value of the function and its slope. Okay, and so you construct that tangent line, that's in red, and you follow the tangent line down till you see where it crosses the x-axis. Okay, once you find that value of x, you go back up. You really need to take this x and go back up with it to the function and evaluate the function there. And you see if it's 0. In this case, it's closer to 0, right? Okay, so it's not close enough to 0. So let me change color here for a second. Let me try. How about green? All right. So what you do is you start at this point, and you construct another tangent. The tangent at that point, which would be about like that. Okay, and you find out where it goes to 0. There's your next guess. You go back up and check the function out. And so you would start here. I'm going to do this all over again. And now I've got another guess. You say, well, it's not close enough to 0, so you keep doing it. So what you're doing is you're using the slope along the curve, driving with that slope down to where the tangent line is 0, hits the x-axis. That gives you another value to try. You take that back up to your function and say, am I close enough to 0 yet? No. Then starting at that value of x, you construct another tangent line, and you keep doing that successively. Okay, I'm going to say that again. Your function is in blue. You want to find out where it crosses the x-axis. That value of x is the root of your function. You start at some value of x as a guess. At that point, you find the tangent line to the function. That's the red line. You trace the tangent line down and find out where it crosses the x-axis. At that value of x, you go back up and evaluate the function at that value of x and see if it's close enough to 0. If it's close enough to 0, you stop. Otherwise, you do the same thing again. You make another tangent line through that point, check out where it is 0, go back and check the function out at the new value of x. If it's close enough to 0, you stop. When this method works, it works really fast. Sometimes it doesn't work. At first, it seems like it could be a lot of work having to construct these tangents, but we can use algebra to make the process easier, so we don't have to be drawing all these lines. We can just start evaluating things. So here's how we do it. Here's the equation for the tangent line at the point x1. The tangent line would go through the point at f1. It would have a slope that equals the slope of the function there, and then it multiply x minus x1. This would draw that tangent line. Let me go back and show you what that line is on the previous slide. Okay, on this slide, that y equals expression I had on the other page, it would draw the red line. It would draw this red line. Okay. So we have the equation for the tangent line. And if we extend this line until it crosses the x-axis, we're going to call the place where it crosses the x-axis x2. Where it crosses the x-axis, the y is 0. So when this function, when the x here is x2, the function is 0. Okay, now we can just solve for x2. And here's what we get. x2 equals x1 minus the function at x1 divided by the first derivative of the function at x1. All I did was take this equation here, and I isolated the x2, and I got this equation. So as soon as I find x1, I could just plug into this formula and find x2. I don't have to draw lines. I don't have to try to have a big solution to an equation. This is just a linear equation. Here's my answer. From x1, I immediately find x2. So if I repeat the process using x2, now I can find x3 by using that same formula. And here's the formula in general. The new point equals the old point minus the function at the old point divided by the derivative of the function at the old point. And after a while, if this method is working, then you will find the value of the function becomes approximately 0. Then xn is the approximate root of the function. Notice up here, if xn is 0, if the function is 0, then the n plus 1 is equal to x to the n. So your values of x are getting closer and closer together. In the previous example, using the intermediate value theorem, I showed you how to apply the method to find the root, a value for the square root of 2. So to do that, a function is set up for which the square root of 2 is the answer. So x squared minus 2, its root would be the square root of 2. Fine. This method requires the first derivative. Newton-Raphson does, so I'll take the first derivative, which is 2x. Now I'm going to plug into that formula. So the next number equals the previous number minus the function at the old number divided by the derivative at the old number. A lot of times when you write these Newton-Raphsons out, you can do some more algebra and simplify things even more. So now all I do is just plug in. I'll start with the number 2. The value of the function actually happened to be 2 here. Okay, fine. But I put the 2 in the equation, and once I work through the equation right here, I'm working through this equation, I put 2 in the equation, I get the number 1.5. I put the 1.5 back in this equation, and I get 1.41 and a whole bunch of 6's and a 7. I put that back in the equation, and I get 1.412156, which is very close to the square root of 2. That took 4 iterations, or actually 3 iterations, and I got my answer. Look at the value of the function. I wanted the function to be 0. It is very close to 0. So when this method works, it works fast. Here's a graph of the process. The red line is the function. I want to find its root. I want to find where it crosses the x-axis. Here's the value out to several decimal places. So I took 2 as my first guess, and so here's 2 right here, and at 2 I constructed that straight line, that straight blue line, and I found out where it would cross the x-axis. That was 1.5. So that was my first linear approximation. So I took this value, put it back in the function, and said, no, it's not close enough to 0. Let me try again. And then I tried again. In fact, I tried several times. But again, draw all of this on one graph. On the next graph, I have kind of zoomed in on this region. Okay, on this zoomed in view, you don't see the starting point. The starting point was 2, and it was way up there. So the blue line was the first approximation, and its answer was 1.5. So I go back up to the function and find at 1.5, the original function in red is not 0. So I try again, and you can see that green line. That was a second linear approximation. See how close it is? And then you can go back up to the function and repeat it. So that is the Newton-Raphson method. I'll show you a couple cases where Newton's method doesn't work. Say you happen to pick a starting point where the derivative was 0. Well, if you construct a tangent line, that would be right here, with a 0 slope, it is never going to hit the x-axis. It will never give you another value. In fact, you'd be trying to divide by 0, and that's not allowed. So a bad first guess. In this case, what would you be looking for? You'd be looking for this point, or this point, or this point. And you could use Newton-Raphson, but you'd have to make a good guess, like start up here, for example, or start over here at 0, and you would find one of those roots. But if you start where the slope is 0, no, it doesn't work. Sometimes things just don't work. Say I want to find well, obviously this wouldn't be so hard. You want to find where x to the 1/3 is 0. That wouldn't be hard because it is 0. But if you start somewhere, I just want to show you a case where it fails. Here's Newton-Raphson, just to review Newton-Raphson. The new guess, get that off of there. The new guess equals the old guess minus this fraction. In the numerator is the function, and in the denominator is the derivative of the function. So you can work that out, and here's what you get for an answer when you go through the algebra there. But if I start with x1 equals 1, I don't converge up to 0. Look what I get. 1, the next one is minus 2, then I get a 4, then a minus 8, then a 16. Obviously this is not going where I want it to. So that was just those were just two examples that Newton-Raphson doesn't always work. If you pick a starting point with a 0 slope, you're like dead in the water before you even start. Okay, and there's other times where some functions it just isn't going to work. Maybe your starting point wasn't good, or the function just isn't suitable for this method. I want to quickly go back and review the method for you. In Newton-Raphson, you have a function, in this case shown in blue, and you're looking for the root of it. That would be this value of x, for which the function is 0. You don't have benefit of this graph, but you can just start algebraically. You pick a value of x to the n. This is your guess. And at that point on the function, you construct the tangent line, which is shown in red. You find out where that tangent line crosses the x-axis. You find the root of the tangent line. Then you take that value and you go up to the function here, and you say, is that close enough to 0? If it is close enough to 0, you stop. If it's not close enough to 0, then you go right through here and you create another. That wasn't very good. You create, I'll just start right on the line, and you create well, third time maybe. Okay. And you create another tangent line. and you check out where that line goes to 0. Well, it's pretty close. So you might be satisfied with that. Otherwise, you'd go back up to the function, right up here, and you check out the function. You could create another tangent line. So you're just going down using the derivative. For the intermediate value theorem, what we did is say, pick a point here where the function's negative, pick one up here where the function's positive, and say, I know that somewhere between here the root is trapped. So take an average. The average might be here, and so I would say the average of those two functions is right here. I'll put it in red. So I take an average of the two values of x, find that right here, and so I'd go up here and say, oh, the function's positive here, so I reassign my upper endpoint to be right here. Okay. Now I would look at those 2 points and say the root's trapped between there. I'll take another average. So you take an average of those two. So you would just kind of successively just kind of cinch down on the root. That was the intermediate value theorem. That was using the intermediate value theorem for continuous functions. Here we're using Newton-Raphson, and that's when it works fast. Okay, and what you do in this case is use a derivative. And you find out where every tangent line goes to 0, and gradually you come into the root. So we can use algebra. Instead of drawing a bunch of tangent lines, then trying to draw another tangent line, trying to draw another tangent line, you can simplify this process by using algebra. And having worked through the algebra, we know that the next guess, x to the n plus 1, equals the old guess minus this fraction involving the function and its derivative. This is suitable for programming. So all you have to do is program this little function in. You don't have to draw lines, draw tangent lines. You don't have to check out a graph. You just do this, and you watch the function get closer and closer to 0, hopefully. And when it gets close enough to 0, then you stop the process and accept that value of x as the root. Or if the two values of x are so close together, you know that you better stop as well.